Okay, yesterday we started to examine convergence tests for positive series. Please underline the term positive because the test we introduced may be applied only for positive term series with all positive terms. So look, recall that we talk about the integral test. And second, we introduce comparison tests. In fact, technically, there are two comparison tests. So we write this. Anyway, so do not forget, we always consider a series of the form where the lower limit is not important. Series may be started by 1 or 2 or 10 or 100. Not important, but upper limit must be infinity. So there are infinitely many terms in the sum. And here, we assume that this is a positive series. Good. So we applied such a test. So integral test, let us remind you that the integral test tells us that, look, the integral, roughly, the integral from n up to infinity f of x dx and sigma an behave similarly. That is, they both converge or both diverge, where f of x is really an when x is restricted to n. Okay? So in the integral test, the strategy is that we find the generating function first, f of x, right? What is f of x? It is a function which reduces to the terms of the series when its argument x is restricted to a positive integer. Of course, there are several conditions on f. It must be positive valued, it must be a decreasing function and a continuous function. And therefore, it must be, in practice, from a practical viewpoint, it must be sufficiently easy so that this integral is not hard to evaluate. Okay? So if this improper integral is convergent, then we conclude that our series under consideration is also convergent. Comparison tests used for positive series, the general idea is that, generally, look, we use the following idea. Similar series, I examine what does it mean similar. Behave or have the same convergence behavior. That is the idea, roughly speaking. This is the idea behind a comparison test. That is, to be more specific, if two series are similar, okay? That is, if two series are similar and the convergence behavior of one is known, then we determine the convergence, of course, or divergence of the second one. Okay? So always, as you understand from the term comparison, in comparison test, we have two series under consideration. In fact, there is originally one series to examine, and we introduce a second series for comparison. This is the general idea. Okay, here is a theorem. Look, we say that we introduce two comparison tests. This first one will be direct comparison test. And the second one, limit comparison test. Let's abbreviate this simply comparison test. And this one may be abbreviated by LCT, limit comparison test. Okay? Now, direct comparison test theorem for direct comparison test. Look, let sigma AN and sigma BN be two series. Of course, with positive, please be careful, positive terms. Therefore, if the series is convergent, the result, the sum, is a positive number. And if the series is divergent, it should diverge to plus infinity. This is the general property of positive series. Okay? Now, usually, let us make a convention between us. Usually, this is the series. We assume that this is the series to be determined. I mean, its convergence behavior is to be determined. Good? And let us assume that as a convention, okay? This is the series we introduce for comparison. Okay? So usually we are given the first series, sigma AN. So we examine this series and we introduce a second series. Let us denote it by sigma BN for comparison. Now, the following is true. First case, if the series sigma BN is convergent, please be careful. The series we introduce must be a series whose convergence characteristics are known. Okay? That is, we know whether it is convergent or divergent. Or we introduce a series whose convergence behavior is known. Okay? So if we introduce a convergent series, yes, for comparison, and if and AN is smaller than BN for all n. So this is a similarity argument. Okay? The two series may be similar in this way. Their entries are smaller than the second one. Okay? This is known. And if this is the case, of course, then sigma AN, which is to be determined, sigma AN is also convergent. okay, by a simple comparison test. Now, this is very obvious. The proof of this statement is very obvious. What is it? Let's say, roughly speaking, of course, both series are larger than 0. Good. And sigma an, because the terms of the second series are larger, sigma an should converge to a smaller number than the sum of the second series, if it is. And sigma bn, this is convergent, good, by assumption, and this is true. So we know that the sum of the first series must be a positive number smaller than the sum of the second series we introduced for comparison. And the sum of the second series, this exists. Sum exists. Okay? This is hypothesis. So, obviously, we can say that our series is also convergent. And there may be a second situation, which is true in this case. If we choose Bn as a divergent series, so which kind of a series should be taken depends completely on the structure of the first series An, sigma An, which is under discussion. Sigma Bn is divergent. So if we choose a divergent series for comparison, and if this is true, this time the behavior, the similarity behavior, or the connection between the two series are something like that. An is larger than Bn for all n. Okay? Good? Now, then similarly, sigma An is divergent too. And the idea is the same. Because An has terms larger than Bn, we expected that An has a sum which is larger than the sum of the second series. But the sum of our second series is infinity, plus infinity, isn't it? We compare it with a divergent series, which diverges to plus infinity. So, and the sum of our series is larger than a divergent series, so it is also divergent by a simple comparison argument. That's all. Okay? For example, so it is basic to find these relations, which is the relation between the terms of the series under consideration and the terms of that we introduce for comparison. Okay? And look, so some mathematical, simple mathematical manipulations can be made to do that. For example, let us introduce a simple example. Examine the series. Let's say from 1 to infinity, 1 over 2k squared plus 3. So first of all, observe that a k 1 over 2k squared plus 3 under square root sign is positive for all k. Right? This is a positive number. So you can apply either integral test or comparison test. But if you introduce integral test, look, you have to, by integral test, in principle, it is applicable, but you have to evaluate this integral. from some number over 2x squared plus 3. So this integral may be difficult to evaluate. So forget about the integral test. Comparison test is better. Okay? Look, so here, observe that. So we have to obtain a relation which is in agreement in the two statements in our theorem about direct comparison test. Good? So we observe that 2k squared plus 3 on the radical side. Let's compare it this one. 2k squared plus 3k squared. Okay? Observe that I multiply 3 by k squared. And k is 1. If k is 1, the 2, and take the square root. When k is 1, the two statements are the same, but in general, this is larger. Good? Therefore, we write this. But the last one can be written as radical 5 times k, isn't it? It is 5k squared, and therefore taking the reciprocal, we have 1 over 2k squared plus 3, okay, using this inequality, is larger than 1 over radical 5 times k. So note that this is nothing but the terms of our series. So by this way, we introduce another series for comparison. Let's say bk. And look, multiplying by some number, the convergence behavior of a series doesn't change. We introduced a theorem for that in the yesterday lectures. Okay, so introduce this series for comparison. 1 over radical 5, 1 over k. For comparison. This is bk, say. Do you know this series? Yes, we say that the series we introduce for comparison must be a series whose convergence behavior are very well known. And actually, this is nothing but harmonic series, which is known to be divergent. Good? So, which is a divergent harmonic series. Harmonic series. Okay? So, now, we have shown that AK is larger than BK. And BK, sigma BK is divergent. So we have case 2 by case B. Okay? Sigma AN, our series. Sigma AN or AK is also divergent by comparison test. Do you understand? So look, sigma, we find that the terms of our series are larger than the terms of a harmonic series. And harmonic series is known as a divergent series. So our series is bigger than, okay, roughly speaking, is bigger than a divergent series, which must also be divergent. Good? Now, another example for every n. So please be careful in applying integral test and comparison test. You have to be sure that the series in question is a positive series. Don't forget. There are only some exceptional cases, only for only a few starting terms may be negative. This is not important. Why? Because the tail is important. The tail of the series determines its convergence characteristic. So if there are some negative terms in first 100 terms, for example, forget about those and consider the tail of the series, which contains all positive terms. Okay? Then you may apply without any trouble comparison test or integral test. Anyway, now look, I'm going to compare this. Again, observe that for this series, observe that. Look, you may use some very simple ideas. An, yes, the entries of our series is radical n over n squared plus n plus 1. And this is smaller than, isn't it? Look what I did. I omit 1 on the denominator, so we get a larger number. Okay? When the denominator is decreased, we get a larger number. And this one, the last statement, can be taken as radical n. Okay? This may be regarded as radical n to power 4 plus radical n squared. So when we simplify it, we get 1 over radical n, or n to the power 3/2, okay, plus n 1/2. Okay, so even you can look. My objective is to find a relation between the terms of our series and a second series, okay, whose convergence behavior are very well known. So one more manipulation. Look, omit this term, n to the power 1/2, which is a positive term in any case, n starts by 1. Please be careful. So we get a larger number, 1 over n to power 3/2. Good? And now, this series is very well known. Do you remember P series? This is the P series. Remember, recall P series. What is the P series? N to power P from 1 to infinity. Okay? And this series is, remember, convergent. When it is convergent, when P is larger than 1, strictly larger than 1, and divergent when P is 1 or smaller than 1. Okay? And the case when P is 1, we have this special case which is called harmonic series, which is divergent. Good? So this is a convergent. Now, let's say Bn. This is Bn. Okay? We can find a series, and hence An is smaller than Bn. So, and introduce the series, the P series, 1 over n to power 3/2 for comparison. Now, everything is very well known. Now, An is smaller than Bn. And the convergence of this series is very well known. So, because by P series, sigma Bn, that is sigma 1 over n 3/2, is convergent. Why? Since P is 3/2 and it is larger than 1. Good? And so then, by comparison test, sigma An is convergent, is also convergent, since sigma An is smaller than sigma Bn. Of course, you should think that this is larger than 0. Why this 0 is important? Do you think about that? Look, sigma Bn has a sum since it is convergent. And the sum of our series is smaller than the sum of P series because of this relation. But if there is no positivity condition, perhaps sigma An is smaller than Bn, but maybe may go up to minus infinity, which also implies divergence. So this is important. So this is why we consider positive series. If the series are not positive, yes, the sum of sigma An may be negative infinity. Okay? So this relation doesn't make any sense. Or it doesn't tell us that sigma An is convergent. But now, in this case, for positive series, we know that the sum of our series is smaller than the sum of sigma Bn, but larger than 0. So it remains a finite number. Good? So that's all. So we find by comparison test that sigma An is convergent. So as you understand, it is crucial importance in a comparison test to choose a correct or an appropriate series to compare. Okay? And of course, you have to know the relation between the terms of your series, original series, and the series you introduced for comparison. That is a relation like that. An is smaller than Bn or An is larger than Bn. So if we say that there is another comparison test, limit comparison test. Here is a theorem. Now, limit comparison test. This is a little bit more practical, okay? The theorem tells us that consider two series again. Of course, positive series. I'm repeating this several times. Sigma An and sigma Bn. And remember our convention. Sigma An is generally the series under examination or under discussion. And sigma Bn is the series that we introduce for comparison. Good? Now, please be careful. In this test, we use the following criteria or following statement. If, look, of course, you have to introduce a second series for comparison again. But if this is the case, look at this limit, which is very easy to evaluate. An first on the nominator, the terms of our series, divided by the terms of the series we introduce for comparison. This is a quantity depending on, and it is generally, it is not difficult to find this limit. Let's say, what about this limit? What can you say about the limit without calculating? Do you expect that it is positive? Yes, your answer must be yes, because an is positive, bn is positive, so the limit of a positive quantity must be positive value. But of course, there are exceptional cases. It may be 0 in an exceptional case. In general, it is a positive number, or it may be plus infinity. Okay? So we have these cases. So where L is positive, but most pedant, to be more pedantic, we have said that where L is positive, okay? L is positive or exceptionally okay, do not consider exceptional cases now. I will give an expression for that. In general, it is a positive finite number where sigma an and sigma bn behave similarly. You know, they both converge, either both converge or both diverge. Good? But notice that sometimes L may be 0 as an exceptional case, or L may be infinity. So a more direct statement must be maybe like that. A more direct, which includes the exceptional cases as well. Okay? I give a statement which includes exceptional cases as well. But usually, if L is finite positive number, two series behave similarly. That is, if you choose a divergent series for comparison, and if this is a positive number, which is generally the case, we have the limit of a positive quantity, then sigma an is also divergent. If you choose sigma bn as a convergent series, and this is true, your series is also convergent. Okay, but a more direct statement which contains this exceptional cases where L may be 0 or infinity, statement is, first, look, if, look, L is positive, but maybe 0, good, including this exceptional case, of course, bounded, L is bounded, L is finite, but maybe 0, okay? If this is the case, you get L positive or 0, and sigma bn is sigma bn, the series we introduced for comparison, converge, okay? Then sigma an also converge. So in the case where we choose a convergent series for comparison, okay, the limit L may be 0. Yes, limit L. In the case of having a 0 limit, the statement is still correct. And a second situation, now, if L is larger than 0, maybe plus infinity, including the other exceptional case for L, if L is positive, finite, or infinity. Okay? And sigma bn diverge. So in the case of the series Bn is divergent, the limit may be infinity also. Yes, and the behavior of the two series are same. And sigma Bn diverge to, of course, plus infinity. Then so does sigma An. So sigma An diverges to plus infinity as well. Okay? But usually we expect that L is a finite positive number, not zero, not infinity. And the behavior of the two series are similar. So if sigma Bn is convergent, then sigma An is convergent. If sigma Bn is divergent, sigma An is divergent. Okay? So perhaps it is useful to give a simple proof for that. Look, roughly speaking, I am going to prove some theorems which helps to understand the material. So what is the meaning of this limit? Remember, we give an idea. You can think that this is a sequence, yes, whose elements are An over Bn. What does it mean? What is the meaning of this limit? Remember the definition of the limit. It tells us that there is some index big N. So when little n is larger than that index, the elements of this sequence are all nearly L. Okay? That is the meaning in practice of having this limit at hand. So roughly speaking, this means that, okay, for very large or sufficiently large values of index n, little n, say when n is larger than big N, okay? In this case, there is a big index n, okay? We have this. An over Bn is approximately L, okay? That is the meaning of, the practical meaning of limit An over Bn when n goes to infinity is L. Okay? Is this. So, this tells us that the terms of the two series are proportional. So they are similar. That is, An is approximately L times Bn. Isn't it? Of course, for n larger than big N. But when you consider the series, look, now compare the tails. You know, tails of series are important for convergence. Good? So compare the tails of two series. That is, when n starts from m plus 1 up to infinity An, and n plus 1 up to infinity Bn. Yes? So these are the tails of An and Bn. And you know, a series behave like its tail. So for n larger than n plus 1, we have this relation between them. Therefore, sigma An, when n is from m plus 1 up to infinity, is approximately L times sigma Bn. Good? Therefore, the two series behave similarly because L is a finite number, a positive number. So the sum of sigma An, first series, is approximately, okay, L times that of sigma Bn. So two series, so two series behave similarly because they are multiple of one another. And we know that if we multiply by a series by a constant, convergence behavior doesn't change. So two series behave similarly. which completes the proof. Very good. Okay. Recall that from a previous example, or in a previous example, we showed that this series 1 over n plus 1, n plus 2 is 1/2. It was telescoping series. Okay? So this is convergent. For a moment, recall this series. So let us examine now this series, 5 over 2n squared minus n plus 4 from 1 to infinity. Please be careful. We choose, so an is 5 over 2n squared minus n plus 4, which is positive. Actually, when n is 1, it is positive, and no problem with this term having negative sign. And look and choose Bn as that 1 over n plus 1, n plus 2, which is, what is that? 1 over n squared plus 3n plus 2. Good? So this series is known as a convergent series, isn't it? A previous example, we showed that. Also, you can show by using direct comparison test that this series is convergent. Anyway, so look, observe that limit an over bn when n goes to infinity. So please be careful. Both an and bn are rational functions in n where the denominator is of degree 2. So it is not difficult to find this limit of the ratio. So an over bn is this limit, n squared plus 3n plus 2 over 5 times over bn an 2n squared minus n plus, and there is 5 here, I guess. N goes to infinity. Good. So this limit is clearly, look, we have two polynomials of degree 2. So we compare their dominant terms. We have 1 over 2 and multiplied by 5. This limit is 5 half. So this is L. As we expected, it is finite and positive. So by limit comparison test, two series behave similarly, and since we know that this series, we prove it before, we know that by limit comparison test, sigma an is also convergent. They behave similarly, and sigma bn, look at that, let's say this is bn. Good. This is bn, as I said, is known as a convergent series. So our series is also convergent. Okay, here is another example. We want to examine the series where an, look, an is cosine 1 over n over radical n. So please be careful in a series where the terms contains cosine or sine. Remember, cosine and sine may take on negative values as well. So in order to apply a comparison test, you have to be sure that the series is positive value. And actually, look, here, cosine, observe that. Please be careful. Observe that cosine 1 over n is always positive for n, 1, 2, and so on. Actually, when n is 1, we have cosine 1, an angle which is smaller than pi over 2. Okay? And in the first quadrant, cosine has a positive sign. And when n gets larger and larger, this goes to 0, and cosine 0 is also 1. So the angle 1 over n is some angle between 0 and an angle smaller than pi over 2. So in any case, cosine is positive for all n. 1, 2, and so on. So we can apply a comparison test. Good? Now, also, you may choose the P series. Choose P series with P 1/2, as you see here. This one, that is 1 over n radical to radical n, or 1 over 1 n 1/2. This is the P series with P 1/2 for comparison, which is divergent Why? Why it is divergent? T is 1/2 and it is smaller than 1. Okay? Which is divergent for comparison. For comparison. So, by limit comparison test. Good? We have this limit to evaluate. N goes to infinity. An, so cosine 1 over n over radical n. This is an over bn. So take the reciprocal of this. Okay? This and this cancel each other out. And what is this limit? N goes to infinity. So cosine is a continuous function. So this is cosine limit n goes to infinity 1 over n. Yes, cosine x is continuous. So this statement is true. First of all, you can take its argument and then evaluate the function. Continuous function theorem for the limit. You have to know from calculus 1. A property you have to know from 119. So this limit is clearly 0, and cos 0 is 1. So L is 1, a finite number. So two series by limit comparison. Two series behave similarly. Thus, sigma an, our series, cos 1 over n over radical n is also divergent. Right? Okay. We'll continue after the break in the next video.